Hello, this is Stat 134, Lecture 11. Last time we started Section 3.2 on expectation. Remember that the expectation of a random variable is the center of the data. In other words, it's a weighted average of the values of that random variable, weighted by the probability of those values. So if x is a count, a strategy for finding the expectation is by writing it as a sum of indicators. Its subtlety is that even if those indicators are dependent on one another, the expectation of an indicator is an unconditional probability that that indicator is 1. So, for example, if x is a hypergeometric random variable, for example, the number of aces in a poker hand from a deck of cards, x takes values 0, 1, 2, 3, or 4, and we can write x as a sum of 5 indicators, where, for example, the third indicator is a 1 if the third card is an ace. Now, the probability that the third card is an ace is 4 over 52. That's an unconditional probability. So then the expectation of x is just the number of indicators times that probability. Today, we're going to give another example of indicators, talk about the tail sum formula for expectation, and also Markov's inequality. So I didn't do this example in class, but I should have. Consider a well-shuffled deck. What's the expected number of cards before the ace of hearts? Let x be the expected number of cards before the ace of hearts. So then x takes values 0, 1, 2, up to 51. And intuitively, if you take the ace of hearts out of the deck, intuitively, it should be about half the deck is before the ace of hearts and half the deck is after the ace of hearts, right? Just by symmetry. There's no reason that on average you would expect more cards to be before the ace of hearts than after the ace of hearts. Let's take a look at this with indicators. So if x is the number of cards before the ace of hearts, we can write that as a sum of 51 indicators, where I3 is 1 if the third card is before the ace of hearts. What's the probability of that? Well, you could think of the third card as being equally likely either before or after the ace of hearts. So I've denoted that by these two slots here. And hence the probability that the third card is before the ace of hearts would be a half. And so we can write the expectation of x as 51 times a half. So then we did this concept test, and it's similar. Consider a well-shuffled deck of cards. The expected number of cards before the first ace is. The answer is B. You can think of it similarly, that if x is the number of cards before the first ace, we're going to write x as a sum of 48 indicators. These are the 48 non-aces in the deck, and the jth indicator is 1 if the jth non-ace is before the first ace. Now, the probability that the third non-ace is before the first ace should be the same as the probability that it's between the first and the second ace, should be the same as the probability is between the second and the third ace, or the third and the fourth ace, or after the fourth ace. So you can think of 4 slots that the third non-ace could go into, and they should all be equally likely. So P would be 1/5, and then the expectation of x would be 48 times 1/5. Then we talked about the tail sum formula for expectation. The tail sum formula is useful when it is easier to find the probability that x is greater than or equal to k than the probability that x is equal to k. And this happens, for example, when x is a max or a min. as one of the main applications of use of the tail sum formula for expectation. So here's how the tail sum formula comes about. When x is a count, 1, 2, 3, and so on, we can write the expectation as 1 times the probability that x is 1 plus 2 times the probability that x is 2, and so on. And so we can write, we have P1, and then we have 2 P2s, and then we have 3 P3s, 4 P4s. And if you look at the columns then, we see that the first column here is the probability that x is greater than or equal to 1. The second column is the probability that x is greater than or equal to 2, and so on. So the expectation then is a sum of these probabilities, giving you the tail sum formula. So application, fair die is rolled 10 times, let x be the max. Find the expectation of x. So we're going to use the tail sum formula here. So just to show you that finding the probability that x is greater than or equal to k is quite reasonable when x is a max. So the probability that x is greater than or equal to k is 1 minus the probability that x is less than k. Now, if x is less than k, then necessarily x1 is less than k and x2 is less than k, all the way up to x10 is less than k, right? So for example, imagine you have a list of 3 numbers, 1, 2, and 3. The max of those 3 numbers is 3. So to say that the max is less than 5, in other words, 3 less than 5, would imply certainly that 1, 2, and 3 is less than 5. So by independence, it follows that we can write the probability that x is greater than or equal to k is 1 minus the probability that x1 is less than k times probability that x2 is less than k, and so on. And all of these probabilities are the same, so we just get 1 minus the probability that x1 is less than k to the 10th power, which is what's given here. And so we can then find the expectation of x quite readily, and we see that it's a number close to 6. We can confirm that as the number of rolls increases, that this number will inch towards 6. Then we did Markov's inequality. So Markov inequality gives you an upper bound for the probability of a non-negative distribution, of the tail of a non-negative distribution. So if a is a positive number, then the probability that x is greater than a is less than the expectation of x over a. So for example, if x is yearly income of Bay Area residents, say that the expectation of x is 100K, then the probability of having a yearly income of greater than 500K, you can easily and quickly say that no matter what the distribution is, it's if the expectation is 100K, then it'll be 100 over 500, or less than 1/5 chance that you make more than 500K. So another example, if x1 to x100 are independent, identically distributed Poisson, remember that the sum of independent, identically distributed Poisson is Poisson. So we would know that the S is Poisson 100 times 0.01, or S is Poisson 1. So the question is, draw the histogram and approximate an upper bound for the probability that S is greater than or equal to 3 using Markov's inequality. So to draw the histogram, I just use my formula for Poisson 1. And to find the probability that I'm greater than 3, I'll just use Markov's inequality, noting that the expectation of Poisson mu is mu, so the expectation of S is 1, and so the probability that S is greater than or equal to 3 is less than or equal to 1 over 3. And of course, we could have determined what this probability is exactly, just using 1 minus the probability that S is 0, 1, 2, or 3, 0, 1, or 2, And we do confirm that it is 0.08, which is less than 1/3. Finally, if we want to prove Markov's inequality, we need a quick property of expectation that if x is less than y, then the expectation of x is less than or equal to the expectation of y. And Markov's inequality, then the proof of that uses the concept of an indicator. Namely, I'm going to look at the indicator where x is greater than or equal to a. So then the a times that indicator takes two values, a when x is greater than or equal to a, and 0 otherwise. So the graph of this a times indicator is the step function shown here. It takes the value 0 if x is less than a, and takes the value a if x is greater than a. And notice that that's always under the diagonal line. So what that tells us is that a times the indicator is less than or equal to x, and so applying expectation on both sides, we get Markov's inequality right away, because we can pull out the a, and the expectation of the indicator is the probability that x is greater than or equal to a, and voila. So I hope you have a great